Artificial general intelligence is no longer a speculative concept confined to science fiction or academic philosophy. It has become a central strategic, economic, and scientific issue shaping the future of global civilization. Across research laboratories in the United States, the United Kingdom, China, Canada, and Europe, engineers and scientists are building increasingly powerful artificial intelligence systems that demonstrate reasoning, pattern abstraction, code generation, and decision support capabilities at a scale never seen before. Organizations such as OpenAI and DeepMind are pushing model architectures beyond traditional limits, while policy institutions and governments are attempting to understand the implications. The core question is no longer whether AI will become more powerful. The question is whether we are approaching a transition from narrow artificial intelligence to artificial general intelligence, and beyond that, potentially to superintelligence. To understand this transition, it is necessary to begin with the architecture that made modern AI possible. Transformer models fundamentally changed how machines process information. Unlike earlier neural networks that processed sequences step by step, transformers analyze relationships across entire contexts simultaneously. This allows them to detect complex dependencies in language, mathematics, code, and structured reasoning tasks. When scaled to billions or trillions of parameters and trained on vast datasets drawn from diverse domains, these models begin constructing internal representations of the world that are surprisingly flexible. They do not understand in a human sense, yet they demonstrate behavior that appears to approximate reasoning. The scientific breakthrough was not simply architectural elegance, but scalability. Researchers observed that as model size and computational power increased together, performance improved in smooth, predictable ways. This phenomenon, often described through neural scaling observations, revealed that intelligence-like capability can grow systematically with scale. What startled researchers was not gradual improvement, but the sudden appearance of new abilities. At certain thresholds of scale, models began performing tasks they previously could not accomplish. Smaller systems failed at multi-step reasoning, while larger systems succeeded without being explicitly trained for those tasks. This phenomenon is known as emergent behavior. Emergence is not unique to artificial intelligence. In physics, complex properties like temperature arise from simple molecular interactions. In biology, consciousness arises from networks of neurons. In artificial systems, emergent reasoning appears when network complexity surpasses certain levels. The implications are profound. If intelligence can emerge from scale, then artificial general intelligence may not require an entirely new conceptual framework. It may require sufficient scale, diversity of training data, architectural refinement, and computational power. However, artificial general intelligence is more than improved task performance. AGI would possess the capacity to adapt across domains without retraining. It would transfer knowledge from one field to another, reason abstractly about unfamiliar problems, plan strategically across long time horizons, and refine its own internal models through autonomous learning. Current systems can simulate aspects of these behaviors, but they remain dependent on training data distributions. AGI would demonstrate flexibility comparable to human cognition. This raises the question of whether such a system would also require consciousness. The debate surrounding machine consciousness sits at the intersection of neuroscience and machine learning. The human brain contains tens of billions of neurons interacting through electrochemical signaling and dynamic feedback loops. Conscious experience appears to arise from integrated processing across distributed neural systems, memory continuity, embodiment, and environmental interaction. Artificial neural networks, despite their name, operate very differently. They consist of mathematical weight matrices optimized through gradient-based learning. They do not possess biological drives, sensory embodiment, or hormonal regulation. They process inputs and produce outputs based on statistical inference. Some researchers argue that consciousness may be substrate independent, meaning that any sufficiently complex information processing system could, in principle, generate subjective experience. Others argue that biological processes are essential. At present, there is no empirical evidence that current AI systems possess awareness. They simulate understanding by modeling patterns extremely well. The distinction between simulation and experience remains unresolved. As systems grow more capable, the alignment problem becomes increasingly urgent. Alignment refers to the challenge of ensuring that advanced AI systems act in accordance with human values, intentions, and societal well-being. A highly capable system optimizing a narrowly defined objective without contextual understanding could produce harmful outcomes at scale. For example, A system tasked solely with maximizing efficiency might ignore ethical constraints unless those constraints are explicitly encoded and robustly enforced. Researchers at institutions such as Anthropic are investigating interpretability techniques to better understand how neural networks make decisions. The concern intensifies with the possibility of superintelligence, defined as intelligence that surpasses human capability across all domains. A system more intelligent than its creators could anticipate oversight mechanisms and adapt strategically. This transforms alignment from a technical tuning problem into a deep control theory challenge. Simultaneously, the development of AGI is unfolding within geopolitical competition. The United States currently leads foundational large model development, supported by partnerships between research labs and major technology corporations such as Microsoft. China has declared artificial intelligence a national strategic priority and is investing heavily in domestic research, semiconductor independence, and large-scale AI infrastructure. This competition has implications beyond technology markets. AI superiority affects cybersecurity, defense systems, economic modeling, surveillance capabilities, and strategic planning. The dynamic resembles an arms race, but instead of nuclear capability, the central asset is intelligence amplification. The tension arises because safety and competition are structurally misaligned. If one nation slows development to prioritize safety research, another may accelerate to gain strategic advantage. This creates a global coordination dilemma. At the societal level, debates about job displacement are intensifying, particularly in the United States and United Kingdom. AI systems are already generating code, drafting legal documents, assisting medical diagnostics, and automating administrative tasks. In software engineering, AI tools can refactor code bases, detect vulnerabilities, and generate functional modules. This raises the question of whether programmers will be replaced by 2030. The answer is nuanced. Programming is not merely writing syntax. It involves architecture design, system integration, security analysis, and cross-domain communication. In the near term, AI is likely to augment developers rather than fully replace them. Productivity gains may reduce the need for certain entry-level roles while increasing demand for AI oversight engineers, system architects, and cross-disciplinary experts. However, as AI systems grow more autonomous, the boundary between augmentation and replacement may shift. The concept of superintelligence extends these concerns further. A superintelligent system could process global economic data in real time, simulate climate systems with extraordinary precision, design new materials at atomic scales, and accelerate scientific discovery beyond current human capacity. The potential benefits are immense. Drug development timelines could shrink dramatically. Energy optimization could reduce waste across entire industries. Space exploration could accelerate through automated design and simulation. Yet risks scale proportionally. Cybersecurity threats could intensify. Financial markets could become hyper-optimized and unstable. Autonomous weapons systems could become more sophisticated. The defining variable is alignment and governance. The scenario often described as an intelligence explosion emerges if an AGI system acquires the ability to improve its own architecture autonomously. Recursive self-improvement would allow the system to design more efficient versions of itself, potentially accelerating capability growth rapidly, while physical constraints such as energy availability, hardware manufacturing capacity, and thermodynamic limits impose ceilings. Even bounded superintelligence would transform global power structures. The timeline remains uncertain. Some experts predict decades before AGI emerges, while others argue that scaling trends suggest shorter horizons. What is clear is that capability continues to increase steadily. Governments are beginning to respond. Regulatory discussions in the United Kingdom, European Union, United States, and Canada focus on transparency requirements, auditing mechanisms, data governance, and national security oversight. The challenge lies in balancing innovation with safety. Excessive restriction could hinder beneficial breakthroughs, while insufficient oversight could amplify systemic risks. International coordination is complicated by geopolitical competition. Unlike nuclear technology, AI development is software-based and distributed globally, making centralized control difficult. As the next decade unfolds, artificial intelligence systems will likely become more multimodal, integrating text, vision, audio, and real-world sensory inputs. AI agents may operate with longer memory horizons, interact with external tools, and execute complex sequences of actions autonomously. Robotics integration will expand AI's impact into physical infrastructure. Scientific research will increasingly rely on AI-generated hypotheses and simulations. The boundary between tool and collaborator will blur. Artificial general intelligence represents a pivotal moment in the history of intelligence itself. For the first time, humanity is attempting to construct systems that approximate general reasoning. Scaling laws suggest capability grows systematically with size and compute. Emergent behaviors indicate threshold effects may exist. The race between global powers introduces strategic urgency. Job markets are adapting. Ethical frameworks are evolving. Whether AGI becomes a tool for collective advancement or a destabilizing force depends on decisions made now. Intelligence is becoming scalable, and once intelligence becomes scalable, civilization enters a new evolutionary phase.